Hello everyone, welcome to robotics module. Today we are going to discuss homogeneous transformation. Here is the outline. First we will have a recap on what we studied last time. Next we will look into rigid motion. The main topic for today is homogeneous transformation. So we will introduce it and we'll have a look at the matrix form, the inverse and the composition rule. Next we will look at some of the salient points that are noticeable and important. And finally, we will do some examples. So last time we mainly looked at rotation representations and we understood the notion of current frame versus the fixed frame. Two main parameterizations of rotations were introduced, the Euler angles and the fixed angles. And finally, we understood certain ambiguities regarding roll, pitch, yaw representation. Now we are going to look at rigid motion. Rigid motion is a combination or a union of translation and rotation. And here you can see it says pure rotation and pure translation. So this one is, let's say, T, and this one you can call as capital R. So what does it mean by a pure translation and pure rotation? So a pure translation means it deals with straight line motion where no rotational influence is there. Okay, so just a basic straight line motion. Similarly, pure rotation means on the spot rotation and no change of origin of the attached frame is involved. So it rotates on the spot and the origin does not change. Okay. Now if you look at this definition, you can see a rigid motion is an ordered pair of T and R, where T is a three-dimensional vector and R belongs to the special orthogonal group that we studied before. And the group of all rigid motions is known as the special Euclidean group SE3. Now there is no sequence we have to follow when it comes to rigid motions. That is, we can either first do the translation and next do the rotation. So here you can see in this animation, you first do the translation and then do the rotation. Or else we can first do the rotation like this and then do the translation. The results would be the same. So the order does not matter in rigid motions. Now I'm going to represent a point P in zeroth frame with the intention of finding the transformation equation. In order to do that, first we can assume both these frames, frame 0 and frame 1, have the common origin. So in that case, you already know how to write P0, right? P0. And if the frames have common origin, we only need the rotation matrix 0, 1 and P1. And that would give P in frame 0. That's it. It's pretty straightforward and you already know that, right? But the general case is when both the frames do not have a common origin. So you can see in the above figure, so let's say we again want to write P0, okay? And can you try it by looking at the above figure? Okay, so assuming you have finished, so we can think of P0, so we have this P0 vector, so you can write it as an addition of this vector and that vector. Okay, so you can write this final P vector as an addition of this vector. So this is actually T, okay, the translation part of these two frames, and then we have to add this part. Okay, so I can straight away write the translation part, that is T1, let's call that T1 vector, but it should be represented or referenced from frame 0. Okay, when we are dealing with vectors, we have to have them in a common frame or in one frame, right? So the translation part is okay. Now how about the final vector? So we know that P1 vector in frame 1, that is this one, okay, but we want that in frame 0. So just like what we did in this case, where the two frames had common origin, we can use the rotation matrix to rotate that vector into frame 0. So here we can make use of the rotation matrix to rotate that to frame 0, right? Now the final result you have here is the answer. Okay, so you have rotated the P1 part to frame 0, and then we have added the translation part. Okay. How about two rigid motions? Let's say we have a point P represented in frame number 2, and we want to represent the point in frame 0. So how do we do that? Yes, we can do the previous operation twice. That means we can first represent point P in frame number 1. So that is this one. Okay, so this is the representation vector of point P in frame 1. And again, we can refer that from frame 0. Okay, so you can use these two equations to finally get the answer for P0. Shall we do that now? Yes. So we can write P0 equals, I'm using the second equation, so I have R01, and for P1 I can substitute from the first equation, and I can write R12 P2 plus T12, and then I have T01 part. Okay, so this would give me R01 R12 P2 plus R01 T12 plus T0. Now there are a few things we can actually observe from this equation. One is all these vectors are in frame 0. Okay, so this one is in frame 0, so this is this green vector over here, right? So this is in frame 0. And this one, so this is T2 vector represented in frame 1, so this one, but it has been also rotated to frame 0 by this rotation matrix. Okay, so this whole thing is in frame 0 as well. And here we have P2, this vector over there. Okay, so first we have rotated that into frame 1. Okay, and after that it has been rotated into frame 0. Okay, so all these parts are in frame number 0. So that is a need to add all these vectors, right? Another thing that we can observe here is two rotation matrices. Actually we can have a single rotation matrix where this one and that one cancels using the composition law. So this is finally equal to R02, right? So that is rotation matrix, or the rotation of frame 2 with respect to frame 0. So this is that rotation matrix, and P2 is this vector. So we take P2 vector and rotate it into frame 0. Okay, and after that we have to add these two translation parts. So this one is straightforward because it is already in frame 0, this guy. But this vector is in frame number 1, so it has to be rotated back to frame 0. So this one does that part. Okay, so finally we have this final answer for P0. Now we could have bypassed frame number 1 altogether, and we could have written P0 to be T2 vector, that is the vector of origin of frame number 2 in frame number 0. So you use the 0 superscript, plus P2 vector rotated to frame number 0. Okay, so we could have written that equation as well, just forgetting about frame number 1. Now if we look at both these equations, we see that again R02 equals R01 times R12. Of course that comes from the rotation composition law as well, but for T02, so that part equals T01 plus T12 rotated to 0 3. Okay, so I'm just comparing this guy and that guy, as well as this translation part and this translation part. Okay. Now we are ready to look at homogeneous transformation. We had the following equation when we transformed point P2 into frame 0. Now if I ask you to transform a point in frame number 4 to frame number 0, yes, now that's going to get complicated, right? Just imagine there is a gripping tool of a robot manipulator which belongs to frame number 10, and I want to represent that in frame number 0. So you understand the complexity of the problem. A long sequence of rigid motions, therefore, can quickly become intractable. As a solution, we are going to represent a rigid motion in matrix form. And with that, composition of such long sequence of rigid motions can now be reduced to matrix multiplication. Okay, so we are going to use homogeneous coordinates for this purpose, where a regular 3D vector, let's say we have P0 x, y, z, a 3 by 1 vector, will become a 4 by 1 vector with the inclusion of 1 as the fourth element. So this is going to be, let's call that capital P0 now, because it's going to be using homogeneous coordinates, and we have x, y, z, and as the fourth element we'll have 1. Okay, and the reason will become clear shortly. For a single rigid motion, we have the following diagram and the equation. Can you try to put this into matrix form using homogeneous coordinates? Okay, let's do that now. For the left hand side, you would have P0, which is a 3 by 1 vector, and since we are using the homogeneous coordinates, we would have 1, and all together we have 4 by 1 vector. Okay, so this should be equal to some matrix, and we need to have P1, which is also 3 by 1 vector, and in the homogeneous coordinates we would have a 1, so we have a 4 by 1 vector. Alright, so that means this matrix should be 4 by 4. Now if you look at the above equation, we need to have a rotation matrix included in this 4 by 4 matrix. So we can see if we partition this matrix like this, and we can include the rotation matrix R here. This is R01, which is a 3 by 3 matrix, and in order to get the above equation, we need to have T0 part also coming in. So far we have R times P and something times 1, and that something can be T01, right? So we can put T01 here, which is a 3 by 1 vector. Alright, now if we look at the second row or the bottom partition, we have a 1 on the left hand side, right? So this P1 should vanish. So maybe we can have a row of zeros here. Okay, so we may put 0 0 0. This is a 1 by 3 vector, and if I put a 1 here, then the left hand side and the right hand side would equal. Okay, so that means we would have capital P0, because we are using homogeneous coordinates, equals, let's call this matrix capital H 0 1, and we have P1. Okay, now we need to confirm whether the newly introduced homogeneous matrix would work for two rigid motions or not. Let's say we have P2 in frame 2 in homogeneous coordinates. Okay, so we have P2 and a 1 in homogeneous coordinates, and in order to transform this into frame 1, we would pre-multiply this with a homogeneous matrix. Okay, so I can have a homogeneous matrix, and I will use the partitions for our convenience. So I have zeros and a 1, and if we are transforming from frame 2 to 1, we have our 1 2, and the translation part P1 2. Okay, so altogether this is capital P1. Agree? Okay, now we can transform this point again to frame 0 using a homogeneous matrix. So we can pre-multiply it, and we can have the partitions for our convenience. So we have zeros and 1, and since we are moving from frame 1 to frame 0, we should have the rotation matrix 0 1 and the translation 0 1. Okay, now let's check what we get as the result. So we can have a resulting matrix and P21, right? So we can multiply the elements, and let's see what we get. So first we have R01 times R12, and the remaining is 0, so that is our first element. Second, we have R01 times T12 plus T01. Okay, and third we have 0 times the rotation matrix and 1 times zeros, so again we would get 3 zeros here, and finally we have 0 times T plus 1 times 1, so we get 1. So you can see the resulting matrix seems to be a homogeneous matrix as well, and we can see when we partition it like this. So here we have zeros and ones and some terms, and in fact you can see this over here is again a rotation matrix. Okay, and this over here is a 3 by 1 vector, and we have the zeros and we have a 1. So the resulting matrix is again a homogeneous matrix, right? Now we have to confirm whether this gives the required solution, that is whether this agrees with this equation or not. So if we multiply this matrix with this one, what we get is this times P2 plus this times 1. So in fact that is what we have here, right? So that should be equal to P0 and finally we have 0 times p2 and 1 times 1, which is a 1, right? Okay, so this agrees with our equation, and you can see a sequence of rigid motions can be converted to multiplication of homogeneous matrices. If I summarize the homogeneous transformation matrix, we have a rotation matrix and the translational vector. So this gives the rigid motion, and at the bottom we have a 0. So in fact this is 3 zeros, so it's like a 0 vector, and a 1, right? So the rotation R belongs to special orthogonal group of 3, right? 3 by 3. Then translation belongs to three-dimensional vectors R3. Okay, so here we have 3 by 1 vector, and we have a 0 vector here and a 1. Right? So the resulting homogeneous transformation matrix is a 4 by 4 matrix. Okay, so we have zeros here, a 1 here, and here we have the usual rotation matrix, right? 1 3 R2 1 2 2 2 3 3 1 2 3 3, and here we have the translation part. Okay, just like we have basic rotation matrices, we can think of basic homogeneous transformation matrices as well. So can you think of a basic homogeneous transformation matrix for pure translation in x-axis? That is, I want to find a H matrix that gives me translation of, let's say, A distance in x-axis. Can you do this? Okay, so assuming you have finished, again we can think of the partitions. So we would have zeros here and a 1 here. Okay, so when we say pure translation, there is no rotation involved. Okay, so the resulting rotation matrix should be identity matrix, right? So here we have the identity matrix. Okay, what about the translation? So it says pure translation in x-axis A distance. So that would give me A 0 0. Simple as that. Okay, so now we have a basic homogeneous transformation matrix for pure translation in x-axis. Now you should be able to do the second one, pure rotation in x-axis. So that is rotation about x-axis, let's say alpha angle. Okay, can you find that? Yes. So again, you'll have the partitions 0 0 0 and 1. When we are dealing with pure rotations, there won't be any translations, right? So it's on the spot rotation. So the translation part should be 0. And you know the basic rotation matrix about x-axis alpha angle, right? So we can fill that up here. So it's going to be cos alpha minus sine alpha and cos. Okay, did you understand that? You can find the basic homogeneous transformation matrices for the remaining 4 cases. That you can do as an exercise. And this is also exercise. How about the inverse of a homogeneous transformation matrix? Now using H01, if we can transform a point from frame 1 to frame 0, then using its inverse, we should be able to transform a point in frame 0 to frame 1, right? Let's try to invert the homogeneous transformation matrix. Now we can use some results from linear algebra where the inverse of a block matrix is given as follows. So shall we use this to find the inverse of H? Okay, so if you take the H matrix, say we have H, so it equals a rotation matrix, translation 0 and 1. Okay, so if you consider this H matrix, you may observe that C equals 0, right? So this one over here, and D equals 1, right? This one over here, right? So using these two facts, we can simplify this expression a little bit. So we get H inverse to be, can you take some time to find this? So you can see this guy here equals 0, this guy equals 0, this 0, and this is also 0, and this over here, right? So what do you get when you simplify this? So our first element would be just A inverse, right? Because you can see this is 0, so this whole thing would become 0. So we are left with only A to the power minus 1, right? And here this is 0 and this is 1, so that would, this whole term would be 1, and 1 inverse is again 1, so we have this, right? So we have minus A inverse times B. Next, here this is 0, therefore this whole thing would be 0, right? Finally, this is 0, so we have a 1 here, 1 inverse is 1. So one thing is confirmed, that is this H inverse matrix, this one, is again a homogeneous transformation matrix. So here we have a 0 and a 1, and you may see this is a rotation matrix as well, and this is some translation vector. Okay. Now shall we use this simplified version of the H inverse and find what the result would be? So we have H inverse equals, so A equals R, so we get R inverse, right? This is 0 and 1, of course. Then the remaining term would be minus R inverse and the translation of term. Okay, so that is our inverse of H, and it also equals to R transpose minus R transpose T, 0 and, right? So given a H matrix or a homogeneous transformation matrix, now you know how to find its inverse, right? So here now we have an equation to find its inverse quickly. Let's have a closer look at the inverse H matrix that we derived. So for H01, we had R01 and T01. Okay. The inverse matrix that we just derived for H01 had R01 inverse and minus R01 inverse times T01. Let's try to simplify this further. So I can write H01 inverse equals, so what do I have here? R01 inverse. That's R10, right? That we learned from rotation matrices. So I can write this as R10. And of course I can fill these two entries as well. Now again I have R01 inverse here that can be replaced by R10. Let me do it as well. So R10. Now I'm going to include that minus sign together with T01. So I can write minus T01 as another vector. Okay. Now let's try to understand what this means using this diagram. Okay. So you can see there is a translational vector T1 expressed in frame 0. Okay, so it has a certain direction and magnitude. Then what is minus T01? So it's going to be a vector with the same magnitude but in the opposite direction. So I can call this vector as minus T01. It's important to note that this minus T0 vector is still in 0th frame. It is expressed still in 0th frame. Okay. Now you can see there is a rotation matrix R10 in front of them. So what would that do to this vector? Yes. So this vector which was expressed in 0th frame can now be expressed in frame number 1 using this rotation matrix. Okay. So what will be the resultant of this? If we are talking about this vector with this magnitude and this direction, and if we are expressing that vector in frame number 1 using R10, what would that become? So will you agree if I write this T10? So it's this T0 vector expressed in frame number 1. Got it? Okay, so I have a matrix with R10 and T10, just similar to what we have here. So what is this matrix then? So it's going to be H10. Okay, so we proved that H01 inverse is equal to H10, similar to what we had in rotation matrices. Okay, so that's an important result as well. However, you have to remember that H01 inverse is not equal to H01 transpose. Okay, unlike rotation matrices. Similar to 3x3 rotation matrices, the same composition rule applies for 4x4 homogeneous transformations. So let's say we have a H matrix that relates two frames, and if we perform a second rigid motion H relative to the current frame, what we would have is H02 would be equal to H01 times that rigid motion that we performed, and since we are dealing with the current frame, we will have post multiplication. And similarly, if we are doing the second rigid motion with respect to the fixed frame, then the resulting homogeneous transformation matrix would be H in front, right? So this is pre-multiplication. Okay. Next, I want to draw your attention to some very important scenarios we encounter with homogeneous transformation matrices. Let's say I have two frames, frame 0 and frame 1, I can use the H matrix H01 to fully describe the transformation between these two frames. So I had H0 equal to R01 T01 01. Okay. Now we saw that a rigid motion consists of a pure translation and a pure rotation, and the order did not matter. So we can first do the pure rotation, and that can be followed by the pure translation, or else we can first do the pure translation and next do the pure rotation. So that means we can write H01, which is equal to R01 T01 01 as two operations followed one after the other, right? Two basic operations. So this is a composition of two operations. First, let's take the case number 1, where we do a pure rotation first, which is followed by a pure translation. So here in this figure you can see, once we do the pure rotation, we get frame I, which is the intermediate frame, and with that orientation we do the pure translation. Okay, so we can write this two operation as a multiplication of two H matrices. So first we would have R0I, and there's no translation, therefore this should be 0 0 1. Okay, which is followed by a pure translation, so there won't be any change of orientation, so the rotation matrix would be I, and the translation would be I1 0 1. Now here you can see we have used post multiplication, where the pure translation happens with respect to the current frame or the frame I. Okay. Now one thing is we need to get rid of this I, right? We need to get rid of I. Okay. In order to do that, let me first ask you a question. Can we replace R0I with R01 and TI1 with T01? So the answers are yes, 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 no, no, yes, and no. So what do you think? So we'll first check with the rotation matrices. Okay. So what about R0I and R01? Now we can see from the above figure that frame I and frame 1 are in the same orientation. Therefore, these two rotation matrices should be equal. Okay. Then what about TI1 and T01? So we have a vector T1 expressed in frame I, and we also have the same vector T1 expressed in frame 0. Can they be equal? No, right? Because frame 0 and frame I have different orientations, therefore these two can't be equal. So they are not equal. So the answer is yes and no. Okay. I can substitute for R0I with R01. So with that I can write this to be R01 0 1 0 followed by I T I 1 0 1. Okay. Let me write the left matrix as it is. So I have R0, 1, 0, and these three entries. Now if I take Ti1, that is this T1 vector expressed in ith frame, now I can introduce a rotation matrix and represent the same thing. So I can have Ri0, the rotation matrix between frame I and frame 0, and then I can have this to be T01. Do you agree with that? So it's the same thing. So this equals Ti1. Okay, so we'll work this out. So now if I multiply these two matrices, I would get, so the first entry would be R01, and these would now change. So what do we get for this remaining term? So we have R01 multiplied by Ri0 T01 and plus 0. Okay, so that's what we get. So now if we look at this term over here, what we have is R01, which is this one, and it is multiplied by Ri0, which is the inverse of this one. Okay, so if we multiply these two, actually they will cancel off. So these two will cancel off. That happens because of this. Okay, so with that we get R01, 0, T01 and 1. So we managed to get rid of the intermediate frame I, and this is H01, which is what we need. Okay, so the homogeneous transformation matrix H01 could be given by two basic homogeneous transformation operations: pure rotation followed by pure translation. Okay, so that's what we proved. So the case number 2 is pure translation followed by pure rotation, right? So we take this frame and do a pure translation without changing its orientation, and finally do the orientation change using a pure rotation. Okay, so for that we can again write it as two basic homogeneous transformation matrices. So shall we write that? So this equals, first a pure translation, therefore the rotation does not change, so it would be I01, and the translation would be T0I, right? So again we will have that intermediate frame, right, which is followed by the change of rotation, that would be Ri1, and there won't be any translation. Okay, so we post multiplied because using the current frame. Now what can we say about T0I and Ri1, because we again have to get rid of I, right? So we have T0I and T01. So if we look at this figure, we have Ti vector expressed in 0th frame, and we have T1 again expressed in 0th frame. Now since both these frames, frame I and frame 1, have common origin, we are actually talking about the same vector, right? Ti and T1. And when we express these two vectors in frame 0, it's going to be same, right? So we can say these two are equal. And what about Ri1 and R01? So again, if we look at this figure, Ri1 means rotation of frame 1 with respect to frame I. Okay, and this one means rotation of frame 1 with respect to frame 0. Okay, now since frame 0 and frame I have the same orientation, these two will also equal, right? So this happen because 0 and frame I have same orientation. Okay, so that means we can replace these I terms very easily. So we have I, so we have T01, 0, 1, and also this R can be replaced by R01, 0, 0. Okay, so when we multiply these two, we would get R01 and we get T01, 0, and this is H01, the required answer. Okay, now this case was a little bit easier than the previous one. So again, we are saying that given a homogeneous transformation matrix, it can be composed of pure translation followed by a pure rotation. Okay, let's move to the next point. Say we have a sequence of pure translational H matrices. For example, let's say we have translation in X direction A amount followed by a translation in Y direction B amount, and finally a translation in Z direction C amount. Okay, so what would be the resulting H matrix? Since these are pure translations, there won't be any change of rotation, right? So that means our rotation would be I, the identity matrix. Okay, and what about the translation? So the final translation would be a vector consisting of these three values, A, B, and C. So why is that possible? Because we are not undergoing any rotation, so after each translation the axis directions will remain same, so there won't be any problem, and we would get the final ABC vector after doing these three operations. And furthermore, the operations will be commutative. That is, let's say we take the translation about x-axis A amount followed by translation in Y direction B amount. Okay, that would be equal to first do the translation in Y direction followed by a translation in X direction. Again, this is possible because there is no change in the orientation. Okay. The next point is, if we have a pure rotation and pure translation about the same axis, then that's going to be commutative as well. So let me take an example. Let's say we rotate about x-axis theta amount, and it is followed by a translation in the x direction A amount. So this would be equal to translation in the x direction a amount followed by rotation about x-axis theta angle. So this is possible because when we do a rotation about a certain axis, that axis direction will not change, right? So when we move in the same direction, it is same as we first move in that direction and do the rotation about the same axis. Therefore, those are commutative, right? So the resulting H matrix would be, so we have the rotation or theta, the translation part A 0 0. Okay, so I hope you understood those salient points. Let's do some examples to understand what we learned so far. So here you need to find the resulting homogeneous transformation matrix H, and you can see all these rigid motions are performed with respect to the current frame. So we would use post multiplication. So let's begin with the first one, rotation about current x-axis alpha amount, so r x alpha, followed by translation about current x-axis b amount, which is followed by a translation along current z-axis d amount, and finally we have a rotation about current z-axis theta amount. Okay, so we can see the first two operations are done about the x-axis, so we can merge those two. So let's write the resulting H matrix. So the translation is B, so we have that amount, and the rotation is about x-axis, so x-axis will remain same, and finally we have cos alpha minus sin alpha, and cos alpha. Okay, similarly we can merge the final two rigid motions, so we get translation would be d along z-axis, so this is d, rotation is about z-axis, so z-axis would remain same, and finally we have cos theta minus sin theta and cos theta. Okay, so you can find this final answer as an exercise. In this second example, you can see a certain scenario where you have a robotic manipulator, then there is a table, and on the tabletop there is a cube, and we have a camera for visual servoing. Visual servoing means getting a visual feedback. Okay, so you have been asked to find the homogeneous transformation matrices from frame 0 to 1, 1 to 2, 0 to 3, and finally from frame 3 to frame 2. It also says that the camera is placed directly above the cube, and the dimensions have been given. Okay, now let's start doing this. First, we are going to find the homogeneous transformation matrix between frame 0 and frame 1. So for that, we need T01. Okay, so the translation between frame 0 and frame 1. So you can see there's 1 meter translation in y direction and 1 meter translation in z direction. Okay, so this is our translation vector. Next, we need the rotation matrix R01, and from this figure you can see both frame 0 and frame 1 have the same orientation. Therefore, our rotation matrix is simply the identity matrix. Okay. So from these two, we can write H01 to be zero, 1, 1. Okay, simple as that. Next, we have been asked to find the H matrix between frame 1 and frame 2. So frame 1 is here, frame 2 is there. So we can begin by writing the translation vector 1, 2, and that is equal to, so we have minus 0.5 in x direction and plus 0.5 in y direction and 0 in z direction. Okay, and the rotation matrix between frame 1 and 2, again we see both these frames have the same orientation, therefore we can write the identity matrix. Okay, so the resulting H matrix would be this is the translation part and this is the rotational part. Pretty straightforward, isn't it? Next we have to find the H matrix between frame 0, which is here, and frame 3, which is at the camera. Okay, so we can start by writing the translational vector T03, and from the figure you can see that the first element would be minus 0.5, the y element would be 1.5, and the z element is the height, which is 3 meters. Okay, next we need to write the rotation matrix R03. Now we can do that by inspection, so that means we can find where these axes are pointing with respect to 0th frame. So we first take x-axis, so it points towards y-axis, right? So that means our first column should be 0, 1, 0. Okay, next we check the y-axis, so it points towards x-axis in frame 0. Therefore the second column would be 1, 0, 0. Okay, and finally the z-axis, so it points towards negative z-axis in frame 0. So we can write 0, 0, minus 1, and that is our rotation matrix. Now there is a hard way of doing that as well, which is, so R03 would be equal to, take frame 0 and rotate that frame about z-axis 90 degrees. Rotate about z-axis 90 degrees, and in the new frame we can rotate about the new x-axis 180 degrees. So since we are using the current frame, it will be post multiplication, so this will be 180. So we first rotate about this z-axis 90 degrees, so x would come here and y would go there. Then we would rotate about this new x-axis 180 degrees. So Z will come down and Y would come in this direction, right? And if we do that, here we can write the basic rotation matrices for these two. So we get 0, 1, 0, 1, 0, 0 and 0, 0, 1 multiplied by the basic rotation matrix about x-axis. Okay, so we would get this should be -1, 0, 0 and -1, and we can multiply these two to get our 0th. Okay, you can later check that. So our final H matrix would be 1.5 and 3, and the rotation matrix was 0, 1, 0, 1, 0, 0 and 0, 0, -1. Okay, so this is H03. Finally, you have to find the H matrix between frame 3 and frame 2, so that would be H32, and that you can find as an exercise. Okay, so whatever the camera sees, all that information would be represented in frame number 3, right? And in the previous slide, we found the transformation between frame 0 and the camera frame 3, right? So now you can interpret what camera sees in the world coordinate frame. Okay. With that, we have come to the end of this lecture. Let me summarize what we studied. So we defined a rigid motion by combining a pure rotation with a pure translation. So the order did not matter. We can first do the rotation and then do the translation, or we can first do the translation which is followed by a pure rotation. Now, using homogeneous transformations, we can convert the rigid motions into matrix form, and in particular, a sequence of rigid motions could be represented using matrix multiplication. And similar to what we had with rotation matrices, if we are doing a transformation in the fixed frame, then we would pre-multiply the matrices, or else if we are performing an operation with respect to the current frame, we would do post multiplication. Thank you very much.